Okay, let's go to present the solution to this problem. We have a function that is the temperature. It's a scalar function. The temperature at any point xy is T of xy x divided by x squared plus y squared. Okay, and what we want to find is first the direction of the greatest increase in heat. If this is the temperature, the insect that we are imagining that are on the surface on the plane xy will move in the direction of the greatest increase in heat, and the direction of the greatest increase in temperature in heat is in the direction of the gradient of the function. And this is a vector function, a vector field. This is a vector field. And what is the expression for the gradient of t? Well, and why? The gradient of t is a vector and is defined like the derivative, the partial derivative of the function of the t respect to the x in the I direction plus the partial derivative of t respect to the y in the j direction. This is the expression for the vector that pointing in the direction of maximum change of the function. And why this is the vector? Well, because as change in t, a change in temperature is the derivative of t respect to the x by t dx plus the derivative of t respect to the y by t dy. So this is the small change in temperature that take place when you move in the direction d dx somehow and d dy. But this can be written like the derivative of t respect to the x, I, plus the derivative of t respect to the y, j, and now we use the dot product. The dot product to produce the left side of the equation. And the dot product will be d dxi plus d dx plus d dyj. And the dot product of the left side, of the right side, will give the right side. So we are defining the gradient of t as this vector, the vector that is between parentheses. So what we are saying is that the change in the temperature is the dot product of the gradient of t by ddr. So why the gradient of t is pointing in the direction of maximum increase? When ddt will change the maximum, ddt will change the maximum when the gradient of t is parallel to ddr. So the gradient of t is in the direction of maximum increase. Remember that the dot product is the magnitude of ddt, of the gradient of t, by the magnitude of ddr by cosine of theta. So if the angle is 0, cosine of 0 is 1, so it means that when the gradient of t is parallel to the direction where you are moving, you obtain a maximum increase in ddt, in the change in the temperature. So that's why these expressions are correct. So let's go to find the gradient of t for this expression. So the gradient of t for this expression will be, let's go to do it by part, will be the derivative of t respect to the x will be t of xy will be x multiplied by x squared plus y squared minus 1. So the derivative of t respect to the x will be the derivative of the first, 1, plus the second, plus the first multiplied by the derivative of the second, which is minus 1, x squared plus y squared minus 2, multiplied by 2x. So we can put it this a little bit nice. X squared plus y squared. We put it here a square, and here we put x squared plus y squared. We didn't do anything. Minus x 2x squared divided by x squared plus y squared squared. And if we sum now, the numerator, it will be x squared minus 2x squared will be minus x squared, so it will be y squared x squared minus 2x squared is minus x squared divided by x squared plus y squared squared. Now we have the partial derivative of t respect to the x. Now we find the partial derivative of t respect to the y, because t of x as y is here. So the partial respect to the y will be x multiplied minus x squared plus y squared minus 2 by 2y. So it will be minus 2xy divided by x squared plus y squared squared. So what is the gradient of t? The gradient of t, the direction in which, if you're sitting down at the point 34, the direction in which the temperature will increase, the maximum will be in the direction of the gradient of t. And what direction is this? Well, let's go to write the vector. The vector is, the gradient of t is x squared plus y squared squared minus, in the I direction, minus 2xy x squared plus y squared squared in the j direction. Okay, and at the point 34, the value of the gradient of t will be 4 squared minus 3 squared divided 4 squared plus 3 squared is 25 squared. 4 squared plus 3 squared is 25, 25 squared minus 2 by 3 by 2, 2 by 3, 6, 24, 64 divided by 25 squared in the j direction, in the I direction. So this is the value of the gradient of t, but the direction in the vector that is in the direction of the gradient of t, well, let's go to simplify a little bit this before going ahead, will be 16 minus 9, which is 7 divided by 25 squared, minus 24 divided by 25 squared j. And the directional, the vector in the direction starting at the point 34 that goes in the direction of the maximum increase will be a unitary vector. Okay, a unitary vector will be the vector 7 divided by 25 squared I minus 24 divided by 25 squared j divided by the magnitude. Divided by the magnitude, which is 7 squared divided by 25 squared plus 24 divided by 25 squared, and here is the same thing. 7, let's go to correct here, 7 divided by 25 squared plus 25 squared. And here the same thing, 7 25 squared plus 24 divided by 25 squared, which is the magnitude of the vector of the gradient at the point 34. So this is the unitary vector, and it has a direction. So it has a direction. You stop at the point 34, and the gradient will go in some direction, maybe like this. Well, here we can see is is positive or negative in the is positive in the I direction, so it will go positive in the I direction and negative in the Y direction, so it will go something like this. So this is the direction of the gradient of t. And this is the direction in which the insect will move on the first step from 3, 4. So our problem was not this one. Our problem was, what is the trajectory that the insect will do? Sorry, in the denominator you need to add the square root, but this is 1 and 1, so it will not change anything. So now the problem is like this. We have a vector field. The vector field is the gradient of t. And the gradient of t is this function, y squared. I'm copying from here, y squared minus x squared divided by x squared plus y squared square I. Minus 2 times xy divided by x squared plus y squared square in the j direction. And the problem is like this. If the insect is going to do a step in the direction of the gradient, what will be the trajectory that he will do if he starts at the point 3, 4? Well, this is the problem. How we can solve the problem? So the problem is find the trajectory that the insect will do. Will do following the increase, the maximum increase in temperature. The maximum increase in temperature, in other ways, following the gradient. So how we will do? So the first way to do it is a computation way to create points that the insects will do step by step. So the idea is like this. The gradient of t is a vector. Okay, let's go to my pen. It's working now. The gradient of t is a vector and it will point in some direction. Now, we have to follow the gradient of t. So we have to make an increment in the position of the insect in such a way that the change in the position of the insect will be parallel to the gradient of t. So to make this parallelism of the change in the position of the insect, so you see, this is the insect. Let's go to do it. This is the insect. This is the R initial. This is the gradient. And I want the insect to follow the gradient. So the R final will be like this, in a way that the change in R is this vector, is this one, this vector. This is the change in R. So I want the change in R to be parallel to the vector, the gradient of t. So I want to be the change in R, small step delta lambda, that will be parallel to the gradient of t, and I want to do it in a way that I will control the step that the insect will do, fixing delta lambda small or changing maybe 10 minus 4 meters, or changing the value delta lambda. So DDR will be parallel to the gradient of t, but indeed is parallel to the direction of the gradient of t, and the direction of the gradient of t is obtained by dividing by the magnitude of the gradient of t. So this is the equation that we work to find the trajectory in a simulation in a numerical way. So let's go to do it again, to write the equations. So let's go to write gradient of t. Let me see, what is the gradient of t here? Is y squared minus x squared divided by x squared plus y squared I minus 2xy divided by x squared plus y squared, square here, and square here, and in the j direction. You see that this gradient, this vector field, is like this. When x is positive and y is positive, like in the case of the point 34, the x component will be 4 squared minus 3 squared, which is positive. So this means that the component x will go in the positive direction. The component y on this quadrant, on this x and y positive, the y component will go always in this direction. So the vector gradient will go in this direction. Now, if you draw a line y equal x, if the point 34 is here, is below the line, but if you are in a point like this, the y will be bigger than the x. 34 is here. Here is 34. If you are here, so here, on this area, on this region, the gradient for a point that is below the y equal x, the component x, because the x is bigger than the y, this will be negative, so the gradient, the component x of the gradient will go in this direction. And the component y of the gradient will go always going downwards in this region, x positive, y positive, so the gradient will go like this, In 3-4, it will go, the gradient will go to the right, the component x, and the component y will go downwards, so the gradient will go like this. So you see, in every region, you can think, for example, you write y equal minus x. You take a point here, and you say to where it will go the gradient. Well, the x components, because the y is smaller than the x component will go, it will be negative, will go like this. And the y components will go, the y will be negative, the x is positive, with this negative will go up. So it will go up, so the gradient of t will go in this direction on this zone. But for a point like this, where the x is smaller and the y is very big, the y squared, the component x, will go in this direction. Interesting. And the y components of the gradient will go up. So it will go in this direction, the gradient of t. This is the direction of the gradient of t in these regions. So you can analyze how it will go, the gradient. Of course, if you take GeoGebra and you put Yeah, I did it. If you use GeoGebra to draw this vector field, it will give you a nice vector field, and is being shown this vector field on the paper that I'm writing. Okay, so what is the question? The question is to find the trajectory that the insect will follow. So we said that we will write this equation. The change in R equal delta lambda, the gradient of t divided by the magnitude of the gradient of t. Let's go to find the magnitude of the gradient of t to make sure that we can do it. So the magnitude of the gradient of t is y squared minus x squared divided by x squared plus y squared plus 4 times x squared y squared divided by x squared plus y squared squared. So the magnitude of the gradient of t will be, they have common denominators, so it will be y squared plus x squared minus 2 times x squared y squared plus 4 times x squared y squared divided by x squared plus y squared squared. So the magnitude of the gradient of t will be 4x squared minus 2. Minus 2 is 2x squared. So it will be y squared plus x squared plus 2 times x squared y squared divided by x squared plus y squared squared. Or in other words, y squared plus x squared squared, because this will be all this again, divided by x squared plus y squared, or y squared plus x squared squared. Wow, this is 1. Well, that means that the gradient of t have a magnitude that is 1 wherever you are, in any point xy, of course, except at the point 0, 0, where the gradient is not defined, because here you can see that the gradient is not defined at the point 0, 0. So, how it will work I'm sorry, there is a mistake on the gradient. I just realized. Sorry, I will correct. Finding the trajectory, so we don't need to write R equal R0 plus the gradient of t. Well, divide by something that is 1, so we don't divide it. So the x is equal x0 plus the component x of the gradient of t. And the component x of the gradient of t is y squared minus x squared divided by x squared plus y squared squared. So the x will go like this, and the y will go the y initial that you put plus the gradient of t. Remember that the r is the vector xi, it's the vector position, xi plus yj. Okay, so the y will be y0 plus the component y of the gradient of t, which is 4x squared y squared divided by x squared plus y squared squared. And now what? And now we do an iteration. The first point x1 will be the initial point, the 3, we start at the point 3, 4, plus the gradient of t. Now the gradient of t at the point 3, 4, so we need to put the gradient of t at the point 3, 4. It will be 4 squared minus 3 squared squared divided by 3 squared plus 4 squared is 5 squared, which is 25 squared. So the point x1 will be 3 plus 16 minus 9, which is 7 squared, which is 49, divided by 25 squared. So I have the first point, x1. And the y1 will be the initial point, y0, the 4, plus the component y of the gradient. So at the point 3, 4, the value of the components, it is 4 by 3 squared multiplied by 4 squared divided by 3 squared plus 4 squared, which is 5 squared. 5 squared is 25 squared. So this will be 4 plus 9 by 16, 4 multiplied by 9 by 16 divided by 25 squared. So I have the second point. How I will do to find another point? The second point, x2, so I have the first x1, the second x1. So it will be the x1 plus the gradient of t evaluated at the point x1, comma y1. So the x1 is 3. Well, I have to, the Excel is being done on the Excel. The Excel will do these calculations. So this is a new number, initial number, plus the gradient of t evaluated at the point x1, y1. So I have this number, so I can calculate y2 like y1, plus the gradient of t, component y, this is the component x, this is the component y, evaluate at the point x1, y1. So I will keep going. x3 will be x2 plus the gradient of t at the point x2, comma y2. And y3 equal y2 plus the gradient of t. Evaluate the gradient of t, the component x and the component y. Evaluate at the point x2, y2. And I will keep going and going. Excel will do the job, and he will find all the points. I have to give him only the initial position, the 3, 4, or changing the position, and he will draw the trajectory on the field. Well, I have to say that this is not what the Excel sheet is doing exactly. What is doing exactly, and the calculation that is being done is here, is the R is the R0 plus delta lambda multiplied by the gradient of t divided by the magnitude of the gradient of t. Now the other question, it will be, can be done analytically speaking? Yes, it can be done. This is the idea of doing analytically. At a point, I have the gradient of t. Perfect. So the insect will move in the direction of the gradient. So the velocity will be in the direction of the gradient. So the velocity, the direction of the vector gradient, the gradient of t. So the velocity will be again parallel to the gradient. So it will be delta lambda, if you want a factor, by the gradient of t. But you see here, there is an angle, alpha. And the tangent of the alpha, of the angle, the tangent of the angle is the component x of the gradient divided by the components y of the vector gradients. But it's also equal to Vy divided by Vx. But Vy is the derivative of y respect to the t, and Vx is the derivative of x respect to the t. So now I have like this. This is the gradient. This is the velocity v. This is v of x, the component v of x. This is v of y. Now when it moves, v of x will perform a ddx, and the ddx that he will perform will be v of x by ddt. And when it moves, the ddy, let's go to put it here in another color. So this is the ddr, so this is the ddy, and this part is the ddx. So the ddy will be vy by ddt. Perfect. So what happened here, that ddx is the derivative of x respect to the t by ddt. And vy is the derivative of y respect to the t by ddt. And ddx, and if you divide ddy by ddx, will be the derivative of y respect to the t by ddt divided by dd, derivative of x respect to the t by ddt, or in other words, is ddy ddt divided by ddx ddt. What I have said is that this quotient is the same quotient that ddy ddx. Oh, if so here I have to write here ddy ddx. So now the equation that I have is that ddy ddx is the quotient of the component x of the gradient divided by the component y of the gradient. And now I have a differential equation when I expect to find who is y of x, whose derivative of y respect to the x is the gradient of t component y divided by the gradient of t, the component y. So in other words, I want to find the solution to this equation. The derivative of y respect to the x equal the component x of the gradients that is here, the component x of the gradient is, the component y is minus 2 times xy, divided by something, minus 2 times xy divided by something, but I don't put it because it's the same thing that it has in the denominator, the x component, y squared minus x squared. Y squared minus x squared. So it's y squared minus x squared. So if I can find the solution to this equation, I will find y of x. But indeed, I will not find y of x. I will find explicitly, I will not find y of x, I will find it implicitly. So what I have done to solve this equation, I'm lucky because it's an homogeneous equation. An homogeneous equation means that if you have a differential equation and you can express in terms of y divided by x, the equation is homogeneous. So we name y divided by x by a new variable that is v of x. V of x, what happened here that it's not writing, let me see. V of x is y of x divided by the line y equal x. Wow. So The derivative of y respect to the x, let's go to see if this is homogeneous. We divide the numerator by x squared, and we have 2 times y divided by x. And because we have divided by x squared the numerator, we have to divide the denominator by x squared. So the equation that I have is that d dy dx equal minus, I wrote the minus 2 times, minus 2 times v of x divided by b squared minus 1. And this is the equation that I will have to find. So what we have to do is we write y of x like v of x multiplied by y2 of x, where y2 of x is x. And what we want to find is who is b of x. If we find who is b of x, we can find who is y of x. So let's go to do it. So I have y equal v by x, v of x multiplied by the function x, y equal x. So in this side of the equation, I have the derivative of y respect to the x. So I want to write it in terms of v. I put it equal to this, and I find v. When I find v, I will find y, because y is v by x. Okay, so let's go to do it. The derivative of y respect to the x is the derivative of v respect to the x multiplied by x plus v of x multiplied by 1. So this is the derivative of y respect to the x. So the differential equation that I have is this one. The derivative of v respect to the x multiplied by x, put it here, plus v of x equal minus 2 times v of x divided by v of x squared minus 1. And I need to find v of x in this equation. Wow. Let's go to do it. Now, to do it, let's go to isolate the derivative of v respect to the x. So the derivative of v respect to the x, or the x, equal minus 2 times v divided by v squared minus 1 minus v of x. So let's go to multiply here by b squared minus 1 divided by v squared minus 1, and I have done nothing. So the x by the derivative of v respect to the x equal minus 2v minus v cubed plus v divided by v squared minus 1. Perfect. And now the numerator will be minus v cubed minus 2v plus v. It will be minus v plus v cubed divided by v squared minus 1. Or in other words, x by the derivative of v respect to the x will be minus v that multiply 1 plus vx squared divided by v squared minus 1. Now let's go to make separation of variables. Let's go to write all that I have v in one side, so it will be v 1 plus v squared, and here will be v squared minus 1. This will go as the numerator, this will go as the denominator, the minus sign, the 1 divided by x, and dx. Oh, and I have found an equation that I need to integrate to find who is v of x. The integral on the right side is easy, it's natural log. So let's go to work the integral on the left side. So let's go to do it. So I have this term, b squared minus 1 divided by v plus 1 of v squared plus 1. And I want to do the integral of this by d dv. How I will do it? Well, I may use partial fraction to do it. So let's go to do partial fraction. So this will be something divided by v plus something b by b plus c divided by v squared plus 1. So I want to find the a and b and c so in this way, this integral of the dv will be this integral, and it will be easy if I can find a, b, and c. So let's go to find a, b, and c. A, b, and c. So if I multiply everything by b multiplied by b squared plus 1, if I multiply if I multiply the left side of the equation by b multiplied by b squared plus 1, I have a, the v will cancel, and I will have b squared plus 1, and I will have here b by v squared plus c by b. This is the equation that I have to solve to find a, b, and c. Now to solve it, I see what's the term that has b squared. The coefficient here is 1. So let me put this together. So it will be v squared minus 1. b squared minus 1 equal v squared that multiply a plus b. Now it will be a plus a, right, plus a, and now plus the term in b, in term b, that is c by b. So because there is no term in b on the left side, the c should be 0. Now the I should be minus 1. And the b squared, the 1, will be a plus b. But a is minus 1. So I have the equation 1 equal minus 1 plus b. So the v should be 2. So I found it, the term. So now I have to do this integral of the dv, this one, and I'm done. Let's go to see what we can find. So it will be equal a, which is minus 1 divided by v, plus b multiplied by v, which is 2v, plus c, which is 0, divided by v squared plus 1. So I have decomposed in partial fraction the integral that I need to solve in order to find the v. So the integral of v squared minus 1 divided by v multiplied by v squared plus 1, I'm following here, by d dv, this will be the minus the integral of 1 divided by v by d dv, plus the integral of 2 times v squared plus 1 d dv. Okay, so instead of solving the left side, we solve the right side. That is easy. So it's minus the natural log of the absolute value of b, plus now I have to find a function whose derivatives 2v divided by v squared plus 1, and this is again a natural value. So it's the natural value of v squared plus 1, because the derivative of the natural value of v squared plus 1 is 1 divided by v squared plus 1, multiplied by the derivative of v squared plus 1, which is 2b, plus a constant of integration. And now remember that this integral that I'm integrating here is equal to this integral. So minus equal minus the integral of 1 divided by x by ddx is correct. So now this is the equation that I have to solve to find v of x. So because the natural log of a minus the natural log of b is the natural log of a divided by v, so this will be v squared plus 1 divided by v. Plus c will be minus the 1 divided by x is the function, the integral is the natural log of x, and I don't need to put any c because this c will englobe all the c's. Okay, so how we will find the v? So the natural log of v squared plus 1 divided by v should be equal minus natural log of x plus c or minus c doesn't matter, is a c. So v squared plus 1 divided by v should be e to the minus natural log of x minus c. And now v squared plus 1 divided by v, and this is e to the minus natural log of x multiplied by e to the minus c. So v squared divided by v is e to the minus natural log of x. So this is e to the natural log of x minus 1. And e to the natural log of x of minus 1 is 1 divided by x. By e minus c, which is c. So this is the equation. V squared plus 1 divided by v is c divided by x. So now we write who is b. B is y divided by x, and the equation that we have is that y squared plus x squared divided by 1 divided by y divided by x equal 1 divided by x plus c. So y squared divided by x squared plus 1 equals y divided by x, which is v, is y divided by x squared c. Y squared divided by x squared plus 1. So y squared plus x squared divided by x squared is c multiplied by y divided by x squared. So y squared plus x squared equals c by y. So we have to complete the square to realize that this is the equation of a circle where the center will be on the y-axis. Let's go to complete the square, and we realize that this is a circle minus c by y plus x squared equals 0, and this term can be written like y minus c divided by 2 square. So now it will appear y squared, that is here, c by y, that is minus 2 times, and it will appear c squared divided by 4. So I will subtract c squared divided by 4 plus x squared equals 0, and this equation 1 and this equation 2 is the same one. So now I can see that y minus c divided by 2 squared plus x squared is c squared divided by 4. Now we need to find who is c. So this is the solution. The solution are circles with radius c squared divided by 4, but we need to write the solution in terms of the initial points. So if the initial point is x0, y0, or what happened here? What happened here? If the initial point is x0, y0, so it means that the point belongs to the solution. So y0 minus c divided by 2 squared plus x0 squared will be c squared divided by 4. So this will allow me to find the c in terms of the initial points. So for any points, for any initial point, I will have a different, a different c. And the c is related with the initial point, x0, y0, like this equation. So let's go to develop is y0 squared plus c squared divided by 4 minus 2 times c divided by 2 multiplied by y0 plus x0 squared equals c squared divided by 4 will cancel with this. So x0 squared plus y0 squared will be equal c multiplied by y0. That it will be y0 here. So I find the c in terms of the initial position. So what we have as a solution is circles with radius c divided by 2, and the center of the circle is x equals 0, y equals c divided by 2. So the solutions depends on the initial conditions and are circles of radius c divided by 2. This is the radius because this is r squared. And center at the point zero comma c divided by 2. For the case that we are studying, so if the initial position is, let's say, 3, 4, so the c will be 3 squared plus 4 squared divided by y divided by 4, or in other words, 25, 4 squared, 16 plus 9, 25 divided by 4. And the solution will be is here, the solution, so c is 25 divided by 4. So the solution for this initial point will be y. It will be y is here. Is the curve? Where is the curve? Is here. Is here. Is y minus c is 25 divided by 4. Y minus 25 divided by 4 square plus x squared equal 25 divided by 4 square divided by 4. So this is the solution. We can represent the solution, and if you go to the spreadsheet, you will find that the solution will do something like this. Well, it will be circles of radius 25 divided by 4, and the radius is 25 divided by 4. This is the 0.34, and it will move in this direction. And if you start at the point minus 3,4, it will move in this direction. Depending on the initial position, you have a circle. The circle, if you go further, if you go to the point, let's say, if you go to the point, to the initial point here, let's say 5, 4, now the center will change. The position of the center, the C will change, so the position of the center will change and will go a little bit up, because the C is now 5 squared instead of 3 squared plus 4 squared. So the C will be higher. So the circles are doing like this. Like this. This is the circle that is doing. Okay. And if you go here in a point, in an initial point like this, the circle will do like this. The solution of the trajectory for the insect will do like this. Okay, so this is the explanation of the problem. Sorry if it was too long, maybe. This gives the idea.